Good morning, good afternoon, and good evening. Welcome to my presentation on the IEEE Vehicular Power and Propulsion Conference 2020. I'm a visiting research fellow from Imperial College and a research fellow from University of Southampton. The research topic to be presented is hybrid propulsion motor drives model based on multi-level multi-cell inverters with optimized fuel economy. Special acknowledgement attributed to Dr. Pietro Cicli from the University of Birmingham for the discussion on multi-level multi-cell converter-based motor drives, as well as the Institution of Engineering and Technology IET for awarding a prize in recognition for my work. Agenda. A parallel hybrid propulsion electric vehicle model is presented with motor drives achieved by cascaded H-bridge multi-level multi-cell inverter modules. The modulation scheme for an 11-level inverter is optimized by minimizing the total harmonic distortions, switching losses, number of carriers, and in the meantime balancing the state of charge between the battery modules. The multi-level inverter model is subsequently integrated into the electric motor drive simulations, with variable frequency adjustable speed and regenerative braking scenarios demonstrated using MATLAB Simulink. Manipulating the electric drives with the regenerative braking, the fuel economy is optimized by keeping the petrol engine operating at a sweet spot, which is 70% to 80% of its maximum torque. Multi-level multi-cell inverter or converter exhibit many properties that make them highly interesting for the hybrid electric vehicle HEV applications. For example, the negligible total harmonic distortions THD in the staircase waveform, which is free of bulky filters. And secondly, the modular configuration with the fault tolerance for the battery pack, such as lithium-ion cells. And thirdly, the bidirectional current control for the battery recharging during the regenerative braking. An 11-level cascaded H-bridge CHB inverter model is deployed in this work and depicted in the figure here, with 5 identical bridge modules connected in series at each phase. The fuel economy of the HEV is linked to the motor drives, and more specifically, the control of the multi-level multi-cell inverter. But its full action and the impact on the hybrid propulsion are only just beginning to be understood. Therefore, a sequence of models underpinning this are developed in this work and characterized by simulations using the MATLAB Simulink. Apart from a majority of the CHB controlled methods based on the phase deposition PWM, this work implements a simple but radical phase shifting PWM, PSPWM, where all the carriers share a same height but horizontally shifted by a specified angle. The circuit to realize this is schematically sketched here in the figure on the left, with 4 time delay blocks for generating the required triangular carrier signals, which is shown in the figure on the bottom right, where each carrier is progressively phase shifted by an angle of 180 divided by 5, which is 36 degrees. It is worth noting that a reversed sinusoidal reference is introduced such that the carrier number can be cut in half for a reduced cost and complexity. Here we show the simulation result of the output voltages. Controlled by the PSPWM proposed, the figure on the top right presents the output voltages of bridges 1, 2, 3, 4, 5, from top to bottom respectively. Synthesizing these voltage steps, the 11-level phase to neutral voltages are produced in the figure on the bottom right. The simulated stator current is shown in the figure on the left. Fast Fourier transform analysis for the stator current is shown in the figure on the right. The nearly ideal sinusoidal waveform without extra filtering demonstrates the advantage of the multi-level multi-cell inverter over the conventional two-level inverters, with further opportunities in multi-objective optimizations, such as using a novel windowed PWM. The developed modulation scheme for the 11-level inverter is subsequently applied to hybrid electric vehicle HEV drives in adjustable speed and regenerative braking scenarios. To achieve the variable speed drives, the generation circuits of the modulation signals are rebuilt to accommodate the requirement of the adjustable output frequency, and in the meantime keeping the ratio of absolute voltage to frequency a constant for the sake of maintaining the magnetic strength of the motor. A ramp signal is introduced to simulate the inverter output frequency, changing from 50 Hz to 30 Hz during the vehicle deceleration from the 9th second. A gain block is inserted to regulate the voltage amplitude in line with the constant volts per Hertz ratio. The voltage and current measurement blocks are introduced in the top left figure to measure the battery average power. The highlight of the simulation occurs from the 9th second when the driver decelerates the vehicle. The frequency of the inverter drops gently from 50 Hz to 30 Hz without steps, and therefore the synchronized speed declines below the rotor speed, which means the motor functions as a generator, as evidenced in the figure on the left. The current direction is reversed, indicating that the batteries are being recharged, which is the regenerative braking, evidenced by the battery power going negative in the right figure. The kinetic energy is recovered and converted into electricity to recharge the battery pack. Therefore, the concept of the energy recuperation is well demonstrated. Based on the regenerative braking model, a parallel hybrid electric vehicle HEV model is orchestrated for the fuel economy. In this figure, we built up a fully integrated simulator for a detailed picture of how the petrol engine can deliver the propulsion in conjunction with the electric motor simultaneously. The internal combustion engine, ICE, is modeled based on an approximate torque speed mathematical function detailed in the figure on the left, where the maximum torque is 150 Nm at 4,200 rpm. The HEV simulator is further developed with the optimized fuel economy by keeping the engine operating at a sweet spot, which is 70% to 80% of its maximum torque. The simulation scenarios are illustrated in the right figure. Accordingly, the control unit, including the throttle demand, is modeled. The focus of achieving the speed variation is put onto the electric motor drives by changing the frequency of the inverter. Here we report the output torque of the engine, which is controlled within a range between 70% to 80% of the maximum rated value of 150 Nm. Finally, the simulation results of the battery power during the vehicle starting, closing, passing, and regenerative braking are reported in this figure. The vehicle simulation well achieves the energy recuperation with seamless driving experience. In conclusion, a vehicle traction simulator of hybrid propulsion motor drives is presented based on phase-shifted pulse-width modulation of a cascaded H-bridge 11-level inverter with adjustable speed and regenerative braking functionalities. Energy recuperation and fuel economy are achieved by the internal combustion engine operating at a sweet spot with the assistance of multi-level inverters to manipulate electric drives. The developed simulating module not only applies for the ground vehicles, but can also apply for the ongoing electrification of airplanes and helicopters with turbine engines as well. Thank you for your attention. If you have any questions, feel free to email me or contact me via LinkedIn or ResearchGate.